Okay, good evening, everyone. I am Priya, one of the organizing co-chairs, and I welcome you all to the third day of week 7 of IEEE Symposium on Data Analytics and Internet of Things. IEEE Victorian section presents this symposium in collaboration with Computational Intelligence Society, IoT Community, and University of Melbourne Student Branch. Just to quickly run you through the schedule of the symposium, it's going to run for one more week until 19th of November, with events happening only on Tuesdays, Wednesdays, and Thursdays, either as afternoon or evening sessions. Like we have one afternoon session next Tuesday as well. Since you have registered for this week, you will be on our emailing list and will receive emails about the event schedule for the next week as well. So you can also follow us on our website and social media pages for more updates. So today's topic is applications and advancement in energy harvesting for IoT systems. The talk will be for around 45 minutes with last 15 minutes dedicated for question and answer session. Please use the question answer tab at the bottom of the window to post your questions. So we have Harvey today as a speaker for this event. Alan has a PhD in image analysis and has worked in power supply design and instrumentation with APM, ENR Sonar, BP Australia and BP UK. He has also lectured in these areas at RMIT in the electrical engineering department. Recently, he's worked on the control systems for the distillation system for converting salt water to fresh water. Thank you, Alan, for joining us today. It's all yours. You can start.
Thank you, Priya. Yes, so tonight's talk will be on principle and applications of energy harvesting for Internet of Things systems. My face will not be on the screen, just simply because my computer it does have a camera, but it is set to off for some reason. So, of course, so an Internet of Things system, what is an Internet of Things system? So an Internet of Things has a set of input devices, switches or sensors, a transmission system, e.g. Bluetooth, Wi-Fi, or 4G mobile, 5G mobile, to a target system at either remote or somewhat locally in the case of simpler systems. So all these things require power. So power supply will drive the input devices. It will also drive the transmission system. And at the far end, normally there will be a separate power supply for the target device. So my background is process engineering, so I tend to think in terms of physical variables. So sensors for light, temperature, wind, water movement, etc. And an example there of a simple Internet of Things system where a mobile phone message may turn on an air conditioner at home, or it may turn on a water for feeding livestock in a farm, and do any number of things by means of a mobile phone message. So here we have some typical sensors, limit switches, and similar devices. So in order to power the Internet of Things system, we need to extract energy from a local variable. Of course, if you're talking about a commercial system, such as a high-rise building, then the energy system is relatively simple. You derive a lower voltage from a power supply for the sensors and for the communication system, etc. However, my talk is mainly on remote Internet of Things systems, where we need to extract power from other forms of energy and convert it to electrical energy. So what are these other variables? Well, without doubt, the most important one is light energy from the sun. Another one is thermal energy, where warm or hot bodies are used to convert to a voltage and which will drive the Internet of Things system. Vibration and motion is another source of energy in which we can transduce to electrical energy. Sensor systems in aircraft very commonly vibrate, so it is common to extract energy from a remote point in the plane from the fuselage of the aircraft and convert that to a small amount of electrical energy. Radio frequency transmissions from microwaves, etc., IF, RF, and broadcast panels, broadcast systems, all radiate energy, which can be converted to a suitable voltage to drive an Internet of Things system. Very often the voltage is nothing like the voltage required, so that there may be a energy harvesting integrated circuit which will convert the usually low voltage of the energy harvesting system to a higher voltage to drive sensors and transmission systems, and perhaps at the other end a final operator for the transmitted signals. Also, a lot of these light sources, or a lot of these sources of energy are not continuous, the obvious one being daylight, which might be 9 hours a day. And so in order, assuming that we need to operate continuously, then there must be battery storage to back up the system at a later time when the sun is not shining. One here is not mentioned is wind power, which we will cover also. So just a brief run through on the input systems and what we're going to look at. Input devices, sensors, energy supplies, particularly off-grid sources, power energy management, energy storage devices, energy management devices. Well, we've repeated that one. Apologies for that. That one and that one are the same. Internet of Things, sensor network, communication systems, energy storage devices, and a summary and references. Okay, sensor types. Sensors vary from binary devices, analog variables, usually which will be converted into digital form by analog to digital conversion system. And so that these things will provide power for the Internet of Things systems. Sensors of interest, portable measurement devices, outdoor systems, such as in agriculture or horticulture, usually are unattended and therefore must be powered by local variables, which need to be continuous. What are we measuring? Well, it all depends on the physical system. If it's a very significant example is an oil refinery, which is essentially a temperature pressure flow industry, then every process vessel, heaters, distillation columns, debutanizers, catalytic crackers, they all have very large numbers of sensors, which are taken back to control units and then used to control those variables. We may also, those are physical variables. Electrical variables, most of us would be well aware of what they are: voltage, current, power and frequency. The smart house, building automation, agriculture, environments, all of those things are important examples for the Internet of Things. Input devices, just a short discussion on those. We know that the sensors will transduce the measurements that we wish to log or use for control. If those sensors are in a outdoor situation, they will not be attended to, and that there needs to be a local source of energy, which is maybe combined with a different systems. For example, a photovoltaic system could be combined with a wind turbine system to generate power and also measure, for example, wind speed. Power requirements. It's very important to ensure that all the devices that you're going to be powering must be capable of being powered down so that you can put them in sleep mode, and also that they only use a very low amount of power when they are energized. So the range, of course, the greater the range of the system, assuming it's a wireless system, the greater the range, the greater the amount of power required to produce a satisfactory signal. It's important to keep data rates as low as possible. Each byte of data requires a certain number of joules of energy to transmit, and therefore the low data rates means a low power requirement. Communication systems, they vary a lot in the amount of power they consume. Mobile phone is probably the most power hungry, and followed by Wi-Fi, Bluetooth and Zigbee, which is a protocol developed mainly for the Internet of Things for sensor data transmission at very low energy consumption or power consumption. Okay, just some more examples of input sensors: thermocouples, electronic transducer systems, which convert temperature to voltage, and resistance devices, which go up approximately 0.4% per degree. This is a resistance element. They produce a very, as I say, about 0.4% change in resistance per degree C. Another commonly used input device is a thermocouple, where you have two dissimilar metals, a reference junction and a voltage out, which is proportional to the temperature being measured. The thermocouple, depending on the metals, has a sensitivity up to 40 microvolts per degree centigrade. So quite a low voltage per degree centigrade. Some other types of important sensors for security, particularly large buildings will have a lot of sensors for detecting movement. So one is a video camera, which detects image differences. And there are, on the other hand, passive infrared detectors, which will detect body heat and therefore don't require their own power supply. Active types, infrared emitting diode sends out an infrared ray, and the reflected infrared signals are picked up. So that if there's a change due to an intruder, then that will be picked up. Ultrasonic detectors, very commonly used. So the sound is reflected back from the moving object, and the Doppler effect will enable you to measure the speed of that object and also detect its presence. Okay, so getting to the energy supply sources for off-grid systems, environmental variables, light energy is, as I mentioned before, the most important one. Photovoltaic systems can convert light energy to electrical energy, and it's at the top of the scale in terms of harvested power per square centimetre. Thermal types the body heat can be used as a source of energy, and whereas industrial thermal supplies produce much greater amount of energy, electrical energy. Vibration, for many of you would be familiar with the self-winding watch, which converted a swinging pendulum into electrical energy, which would then charge a battery, and that would power the watch. Vibrating machines is another source of energy, and it produces a much greater amount of energy per cubic centimetre. At the bottom of the scale is radio frequency systems, where you convert the energy in from a transmitter. You pick up the energy by means of an antenna and convert it into a harvested power electrical signal. Extremely low energy density, depending on the antenna size, etc., etc. So this, along the bottom here, we have the amount of power required by various systems. A watch of the order of 1 microwatt, smoke detector 10 microwatts, occupancy detector 100 microwatts, LCD clock half a milliwatt, glass breakage detector some number of milliwatts, seismic detector 37 milliwatts, of course depending on the construction, headphones 60 milliwatts, and a smartphone 1 watt. So these give you an idea of how much power is required. So down at this end, smoke detectors and occupancy detectors are the power levels you would need for a security system. Okay, so starting off with light sources, solar cells will convert radiation to electrical power. Strong sunlight will give you 100 milliwatts per square centimetre of solar array, which converts to 1 kilowatt per square metre. Of course, that's in strong sunlight, which only occurs for perhaps 8 or 9 hours a day. Again, there's a heavy penalty in conversion efficiency, which start now reaching about 20%, so that 100 milliwatts per square centimetre may end up at 20 milliwatts per square centimetre, or even 10 milliwatts per square centimetre at the low efficiency end. So integrated circuits will, using switching regulated techniques, will convert from these photovoltaic cell levels up to battery charging voltages or a supercapacitor, and it also provides a maximum power point function as well. So these linear devices are used to control, or they're connected to the photocell, and they transduce the voltages to whatever voltages are required for the system. Another important one is a relatively new system, is a PN junction type thermocouple. A PN junction thermocouple consists of a series of PN junctions, often in series to increase the voltage, and the difference in temperature between the hot side and the cold side, and the difference in mobility of electrons generates a certain voltage of the order of 40 millivolts per degree C, and that's a 1 by 10 array, so each one would give you 4 millivolts per degree C, that's right. So because they are a PN structure, they can be relatively easily built in an array, perhaps a 10 by 10 array of 100 PN junction thermocouples. So 100 thermocouples in a 10 by 10 array, or PN type junctions, I should say, will produce 100 by 400 millivolts per degree centigrade. So even relatively small temperature differences, perhaps 10 degrees, are useful in terms of generated electrical energy. Energy harvesting using vibration, as I mentioned before, vibrating machines, vibrating aircraft may use a transducer device in which the relative movement of a magnetic slug inside these coils, the magnetic device inside a north-south pole magnet moving backwards and forwards will produce varying flux lines in these coils here, and which will convert to a generated voltage, an AC voltage, and that may be converted up to useful voltages for an IoT sensor transmitter system. So the principle of it is the magnet inside here will move backwards and forwards because of the vibration of the machine. These coils are fixed to the frame of the machine, and the magnet will move backwards and forwards and vary the flux lines in these coils, which will induce a voltage in the coils. Wind generation, perhaps the oldest form of transducer, converting from wind power to in previous generations to mechanical movement for Internet of Things there, and also for power generation, of course. Wind farms produce a considerable amount of power, green power. Then as the wind goes past the turbine blades, it will cause this blades to rotate, and the vertical axis type also has a similar action. The wind forces it to rotate and turn a rotor inside a magnetic field, and again the rotation will cause flux lines to be cut and generate a voltage in this generator here. So as a rule, there will be a step-up gearbox to increase the number of revs per minute, because the rate of flux cutting will give a more higher voltage by means of the greater number of revs per unit time, and you will then generate a voltage. The amount of power is proportional to the cube of the wind speed. So a 10% increase in wind speed produces approximately a 30% increase in power generated. Note that a 4-to-1 speed range will produce 64-to-1 power range. Not quite sure that's right. 4 cubed, 16 by 4. Yes, that's right. 64-to-1. So it's even with the 4-to-1 speed range of the wind, which is quite common, you'll have a massive range in power generated. Radio frequency energy sources. This is a RF energy is all pervasive. Broadcast signals, FM broadcast signals, AM, FM, television signals, mobile phone signals. All of these can be, the power can be harvested from them, and by means of an antenna, and then a matching network will maximise the amount of power extracted, and then a conversion device, RF to DC conversion circuit, will then produce a certain voltage, and that will then produce the voltage in a DC load, for which will be the Internet of Things, sensors, and Internet of Things transmission system. Some more exotic looking transducers for converting RF energy to local electrical energy, or extracting RF energy and converting it to local form, wired form. This is a loop antenna here, which will use a very large number of turns, which will act like a frame antenna and pick up a varying magnetic field caused by a RF signal, whereas the patch antenna here is essentially operates on the electric field of the microwave signal, its resonant frequency is determined by the ratio of length to width, and its driving point impedance is determined by the distance from the ground plane in particular, and also to a certain extent on the L on W ratio. So those are two antenna types which can be used to extract power from RF signals. Body variables for fitness and or for athletic analysis, there is a great need to extract energy from the human body. So there are various transducers which will produce a electrical energy from a suitable transducer. So we have here some PZT is it's poly zinc something or other. It's a very complicated formula, but it's a type of material which, when flexed, produces an electrical signal. And when a person is running, you have relative motion between the stator and the rotor, and that produces a signal which can be used for driving transducers such as heart rate, body temperature, blood pressure, etc. So this is an example of a sort of a personal method of or body movement powered kinetic energy powered system to extract energy. Okay, so power management devices, power and energy management devices. I'll go through these fairly quickly. An energy harvesting system. We've gone through this might be light, wind power, or temperature difference or vibration. So the energy management system may drive the batteries, which are used for storage of power when there is no energy input, and also provide the signal for the transmission system, and also energy for the transducers. Energy storage devices. Well, there are two obvious ones. Storage batteries. Lithium ion is by far the most efficient one, which is commonly used. Supercapacitors may also be used for energy storage between 0.5 farad and tens of farads. They do have rather a low working voltage though, but however they can store several joules of energy. So in this example, a 10 farad supercapacitor is charged to 5 volts. How long can it supply 1 milliamp? So with that difference, well, it discharges from 5 volt to 3 volts, drop of 2 volts, and that we can work out using I equals CD VDT. That will produce 1 milliamp for 5.5 hours. So if we reduce the duty cycle by, for example, a 100th sample rate, let's say you're measuring the level of a lake and the temperature, then the sampling rates could be quite low, and you can increase that to 550 hours, by using a low sampling rate of 1 in 100. What are these energy storage devices like? Well, the batteries may be integrated on the substrate of the integrated circuit. Obviously, they are a throwaway device. There's an interesting application for or a military application where you detect movement by producing thousands, if not tens of thousands of devices which can detect movement, have an integrated battery, and they may be scattered over an area where you want to detect movement, and then they may last for a week or something of that order, and the energy storage is provided by a lithium-ion cell, which is integrated into the device. They are lithium-ion cells, may be produced in very tiny sizes. You see this single cell here, which is about the size of a fingernail. So they may be used for energy storage. Some network examples, depending on the application, you may have all the sensors of the IoT system connected in star or mesh or combination of both. And if you use a Zigbee system, which is very low power, then that will give you a relatively optimal signal with low energy consumption for transmission of the sensor information, which may be health-based, building automation-based, retail, energy-based, or home automation. Okay, so here is an example of application of Internet of Things to a vineyard, where you can see hundreds of grapevines here, and the energy to drive the measurement devices for air temperature, soil temperature, solar radiation, relative humidity, all those variables are important for growing grapes. Then you need transducers to provide that energy. So this is a generator for coupling to a wind generator. This is a water turbine-based device for producing mechanical rotation of a generator or alternator. And here we have a photovoltaic array. So just a simple block or a simple diagram showing all the different devices which have to be connected. And we have a local cluster of these variables. So it's a cluster network, and then there will be a router which will take all these signals and transmit them via a wireless network using Zigbee type protocol to an environmental monitoring system. It may be used to control the amount of water to these vines, for example, to keep the soil temperature and soil moisture at optimum levels. Okay, just to finish up now, energy supply for Internet of Things systems. Evaluate the Internet of Things input devices required. Ascertain the minimum sampling rates needed choose a network protocol, preferably of a low power protocol. Evaluate the amount of data storage requirements or local requirements. Evaluate the details of display devices or control devices required locally and what controls are required, e.g. turning on water sprays when soil temperature becomes too high. Calculate the system current energy requirements and select energy harvesting devices and battery storage devices to provide power for that system. Calculate the storage requirements for capacitive battery storage based on sort of longer term knowledge of solar radiation, wind, power, etc., etc. Some newer techniques have been mentioned in the IEEE literature. Harvesting energy in the sugar from sweat may be used to power body measurements. Okay, so these are the references. You can get those from the slides. And just one final slide on just how far should we go with Internet of Things. So here we see a couple, the lady standing on the scales. Bad news, dear, the scale is threatening to cut off our access to the fridge. Okay, so thank you, and that concludes my talk on energy harvesting for Internet of Things systems.
Thank you, Alan. Thank you for the great talk. It was very informative. So now we open the floor to the questions. We have the first question from N. He's asking, would it be feasible to deliberately direct an RF wave at an IoT device to power it or charge it, in contrast to scavenging energy from existing RF services?
Could you rephrase the question a little bit? I didn't quite catch the gist of the question.
So he's asking, would it be feasible to direct an RF wave at an IoT device to power it or charge it?
Oh, this is to do with extracting RF energy to power Internet of Things devices. Is that have I got that right?
Yeah.
Okay, yes. Obviously, RF energy is extremely low, and it's only feasible to drive very low power devices, which are available. You can, there are microprocessors which only operate on a fraction of a milliamp, and power management devices which are similar. But yes, the only very low power sensors could be run from a RF energy harvesting system. That's certainly the case. Thank you.
Thank you. So the kind of a follow-up question to that is, are there any specific examples of that, or they're just general microprocessors?
Specific examples, well, certainly in remote locations, such as monitoring of water supply systems, very low power level systems and very low power salinity measuring systems can be energized by a wireless transducer system. However, as a rule, solar systems would be a more practical way of powering such a system. Thank you.
Thank you. The next question is, what are the factors to be considered to get power supply for IoT devices?
Right, okay, so, well, the first step is to, the first step is to design the system. Like, for example, recently I was working on a desalinator system, and there are quite a number of temperature measurements and some flow measurements which are required in order to operate the desalinator properly. So once those measurements are decided, then you need to evaluate the amount of power, particularly current and voltage for each device, and work out the total power budget for the system, and then design your energy harvesting system in order to provide that power. In the case of commercial desalination, you will normally have an on-grid power supply system, so that energy harvesting as a rule won't be needed. But in fact, it is still used in a commercial desalination. The energy in the product, which is distilled water, is at quite an appreciable temperature, and energy harvesting systems are used to extract that energy from the hot distilled water. Thank you.
Thank you. The next question is, can you also throw some light on ultra-low power technology for battery-less IoT sensors?
Some energy supplies for battery lighting systems, was it? Or
Ultra-low power technology for battery-less IoT sensors, like with no battery IoT sensors.
So sensors for lighting, you mean providing, like, you don't mean solar systems, I think you mean battery charging for, or energy harvesting for battery charging. Is that the question that you're looking at?
So the question is, anything which any IoT sensor which does not depend on battery, but on any other sources of power, ultra low power, which uses any ultra low power technology for working.
Well, of course,
instead of battery.
In an off-grid system, to store energy, you will need a battery system, or perhaps a supercapacitor system, which will store the energy extracted by the energy harvesting systems, all depending on the power budget for the system and whether or not it needs to be operated 24/7, or it may only need to be operated during the day. So like schools, for example, or commercial buildings will commonly only operate from, say, 8 a.m. to 9 p.m. so that there's no need for 24/7 power supplies. However, if there are remote sensors in such applications, then the first choice in applications or transducer systems would be probably a solar system for transducing solar energy to electrical energy, perhaps backed up by a battery system and perhaps with wind power as well. So it all depends on the solar power distribution and the position. Of course, in Northern Australia, we have many more hours of daylight, so solar systems will provide a lot more energy per day, so that energy storage systems will be less have lower capacity. Okay, thanks, Priya.
Yep, thank you, Alan. Do we have any more questions? Harvey, do you have a question? I think you wanted to say something in the beginning of the talk.
He's been blinded with science.
Harvey, if you would like to speak, you can unmute yourself and you can talk.
I think he's.
I think we're good.
He's
a
very shy man.
Okay, so then I think we can wrap up the session now. Okay, so thank you everyone for attending the talk, and a big thanks to Alan for taking out time to share his knowledge on energy harvesting for IoT systems. For next week, we have the afternoon session on Tuesday with Dr. Puneet Rathore, who will be speaking on big data clustering with urban analytics at 12 p.m. I look forward to seeing you all next Tuesday and the upcoming events of the symposium. Take care and stay safe. Thank you.
Thanks for all your help, Priya. That was great.
No